Hello, friends, and welcome back to Machine Learning with Cats, Part 4. I guess this is our second day of really getting into sort of the heavy machine learning. Day one was just sort of intro to Python. Day two, we did sort of a simplified version of just a very basic linear regression model. And then yesterday, we really got into, hey, we have image data. How can we really, really make the most of that image data? I'm gonna turn on a little bit more light. Oh, maybe that's too much. Here, let's make it warm. I don't know about you, but recently it's been getting chilly in Seattle. Let's go. Incredible! That's so good to hear that you're able to catch them all, and now you're able to be with us here live. Emily, good to see you. Good to see you. Hello, hello. I'm glad that you're back as well. And I am glad that it's. I don't know. This is the promise of the internet, is that you don't have to be in like the same place at the same time to be thinking about the same things. And so I love that we have two folks that are sort of popping in and out. Let's do our of course standard by this point beverage check. I'm currently drinking some water, but not too long ago I was drinking I'm a coffee nerd, but I was drinking some like diner coffee. And as a coffee nerd, it's like I'm roasting my own beans. I am I'm dialing in the grind level. I'm like playing with pre-infusions, all this random stuff. And then you go to a diner and they're like, this is the random shit that we have in the batch brew. And it's good. It's not like it's a different thing. It's not like, oh, that coffee was so bad, but it's a different thing. And I think I need to taste it every once in a while to appreciate what I'm doing, Yeah, okay. They really, I appreciate that you feel like it's a lot of content, because I feel like this week has been particularly, 5 sessions. For me, it's a ton. But I'm glad that y'all are sticking with me through it. Emily is brewing coffee right now, French press. Love that. French press is the way to go. Getting too old to stay up late here on the East Coast. Yeah, no, that's valid. I guess it's 9 p.m. for you. I may have already shared this story, but when I was most recently living on the East Coast, which was a while ago, when I was in Boston, I really had a cold brew phase, and I'd use my French press. If you're unfamiliar, it's very easy to make cold brew with a French press. You just throw everything in there, stick it in the fridge for a day, 12 hours to a day, and then you just kind of pour it out as if it was French press, and boom, you have cold brew. I was really, really riding high on drinking a ton of cold brew. 6:30 in India. Good morning. Good morning to you, friendo. Oh, good morning to you. Cold brew is nice. Yeah, I agree. MLH is now live streaming talk shows and podcasts. Machine Learning with Cats, Part 4. Here we are. So let's get into it. I guess we're 5 minutes past the hour. Oh, actually, one other update. I did find my cough drops. So I have some cough drops, and probably 20 minutes from now, I will pop one of these in, and it'll be so good. These are, if you're unfamiliar, the Luden's cherry flavored cough drop. It's literally just candy. This stuff is just candy, and I love it. I actually had an experience when I was like 8, and I had heard if you take like medicine you're not supposed to, you can die. And I had one of those, and I was like, wow, this is candy. And so I had 3 more, and then I worried that I was going to like OD on cough drops, because like I wasn't supposed to take 3 of them. I was just supposed to take 1. And I have since learned that it literally is just candy, so it's not an issue. But welcome back. I think I did a little bit of a speed run of what we've done. Day 1 was intro to Python. Day 2 was sort of intro to machine learning with linear regression. Day 3 was sticking our feet in Keras, dipping our toes into Keras. And now we're going to get even a little bit more intense with our Keras models. So I guess to zoom out, the task that we are charged with. Actually, before I do that, I should drop the check-in form. Here is the check-in form. Boom. And then, of course, here is the link to Kaggle. Yeah, they're really tasty. You give one of those to like someone who's 8, and they're like, I don't know what you want me to do with this, but I'm just gonna eat it. In fact, actually, now I've really worked up an appetite for a cough drop. So time for a cough drop. I have 3 of them here with me, so we'll just try to pace ourselves. Oh, so good. So leaderboard. Let's go back to overview. Actually, let's go to data. So our task is to look at the image of a little crypto kitty, like this little guy. This is kind of our mascot because we keep looking at him as the first example. To look at this image and to predict how much the person who is selling this NFT is asking for it. And in our data, we have a label here, so we could find that, and we have a certain price, and this is in Ethereum, and we just want to predict what that price is going to be. And last time, we can pop back into the notebook we were working in last time. Oh, I should also add, this is really the first day. I didn't see many people saying like, hey, this is my first time. It looked like most people who are here have like caught up with us and followed along. It's taking a second to load. But this is the first session, like really, if you weren't here for the previous 3 sessions, if that was your first session, like it was a good entry point. Here today, this is really really not a great like first session to attend. You know, it's number 4 out of 5. So we really are building on what we've done at this point. So if we hop back into image regression with Keras. Oh, actually, before we get too deep into it, at the end of the last session, we were talking about how our results were a little bit unintuitive, and there was in fact I won't be too specific, but there was in fact a bug in the test set. And so I did post about this, but there was a little bit of an issue with the test set, and I fixed it. And so now if you rerun code, like if you just resubmit earlier submissions, you should just get better performance. So actually, if you go over to, let's click in a few ticks. If you go over to the leaderboard, you can see that there's like this break where there are a bunch of people that have like 12 or below, so like really good scores, and then it jumps up to 38. And so all the scores that are like 38 were from before I fixed the test set. So if you had a thing that you're working on and even if you haven't changed it, if you have a score or an error of greater than like 30, try just submitting it again because you will probably get a better score on it now. Right on. Okay, so back to image regression. I want to play around a little bit more with this. So we touched on how what we're trying to do is going from image data to a regression output, so to just some number between 0 and infinity. It's not like a classification or a category. We just want a number out. And we looked at how we could use Keras. Oh yeah, let's manage our active sessions. Stop session. Cool. Yeah, this is a fun fact. You can only use 1 GPU at a time on Kaggle. So if you're running multiple notebooks that require GPU, Kaggle will say, you can't do that. But now we should be able to try again. So I'll tap through some of these just to review. But so we imported our image data. And this time we just used grayscale. We looked at what was inside of our image. It's taking a second to start up. But we use this idea of a dense neural network where we just fed in all of our pixels and all of them got connected by our neurons in our dense layer. So there's the images that we had, sort of simplified versions where the pixels are it's a little bit more pixelated. And we clipped our label values, just sort of tapping through this. Oh, input data is not defined. Oh, there we go. I guess first we trained this very simple model where we just had one set of weights that fed in. Hello, Srivanik. Good to see you. Welcome, welcome. We're just doing recap from yesterday. And we could see that after letting it train for a bit of time, we trained for 100 epochs. Okay. Oh yeah, because we wanted to see if it would change. Maybe we let it go. But then we looked at that first layer of weights, and we saw that by just visualizing that, we could actually get a sense of what the network had kind of learned. And once this finishes running, we'll be able to see that. just by grabbing the, I guess another point that we'll touch on today and tomorrow is that your model, we talked about how Keras models are sort of like Legos where you can piece them all together. And there's nothing stopping you from, after you've pieced a model together and you've trained it, there's nothing stopping you from actually cracking that model open and looking inside, right? Legos are really easy to put together and they're really easy to take apart. So yeah, this was our sort of, if you just visualize the lighter spots are where it has a really high value, really positive value, and the dark spots are where it has a really negative value. And so you can kind of intuit that if there are pixels, if you're lit up in the spots that have really, really light areas, then that actually is really positive for the value of the CryptoKitty, or at least for what it's being, for the price it's being sold at. So valid. Well, I support everyone going to their classes, but yeah, feel free to hop back and watch it at the end. But we will be doing convolutional neural networks today and be introducing image data. The one thing that I hope to get to, but we might not have time, is actually using sort of more complex model architectures where we can stitch together the thing that we had earlier, where we were just using price and doing linear regression, and merging that model and our convolutional neural network. So that'll be probably tomorrow, but we might do it later today. Well, yeah, go to class. I totally support that. So that was just with a single hidden layer. But then we saw, hey, we can have more than one hidden layer if we want to. And so in this scenario, we added, or sorry, that's with a single layer. And here we added a hidden layer in the very middle. And so we gave it some arbitrary number of neurons. We picked 64. And we saw that we trained it, let's only do it 20 epochs here. But we saw that we could, in fact, get better performance. So here, if you look up here, our loss was 11.25 at the end. It kind of oscillated or moved around a little bit. But they were able to get decent performance with this additional layer here. And we saw the parameter count jumped up to 2.5 million parameters. We also saw that we could visualize the loss. So this is sort of like how much error it has over time. And then we played around, or we thought about playing around with the model, and I think we ran out of time. But so we trained sort of a final model. And we use this notion of a validation split. So this is the idea that you don't want to test your model on the same data you trained it on, because that would be just like your teacher giving you the test as the study guide. That's like, well, hey, if you've already seen the test, like you have no reason to learn it. You can just memorize the answers, right? And so having a validation split meant that we would just be testing it on some data that wasn't what we trained it on. That'll take a second to run. And then we made predictions. And so now if you resubmit this notebook, you should get a much better score. But something that I threw out is that we can run an experiment. Someone said, like, yeah, I often don't know, like, what kind of parameters should I use for my, what kind of parameters should I use for my model? What sort of learning rate should I use? Like, I don't know how to set these parameters. And that was something that I threw out that we could get into. Okay, so there you see sort of, this is actually a super interesting graph, because right there you have an example of, oh, that's a moment where like it thought it knew something about data it hadn't seen, and it very much did not, right? So then we generated predictions. This is sort of our final, using that model we just trained to actually submit. But so then I said, what if we do a little experiment? And we could test hidden layer size, but I'm actually kind of interested in testing the number of hidden layers. So let's say n is going to be the number of hidden layers we have. And we will basically just say, okay, so let's have a list of layers. So these are all the Legos that we're going to put into our model. We have a function that we're going to be able to call multiple times. The first step in our function, we're just always going to have be flattened, because that's what we want. But then we'll say for I in range n. So for if n is 0, we won't enter this loop at all. If n is 2, we'll run this loop 2 times. And we will just say we have let's call it a 64 unit layer that we will append to our layers list. So this is the effect of layers will have no dense layers in the middle. If n is 0, it'll have one dense layer in the middle if n is 1, and so on and so forth. And then we'll always finish it off with layers append this dense layer here. So this function, we can call this multiple times, and it will allow us to play around with how many hidden layers we have. Then we can compile it, and then we can fit that model, and we'll just return the history here, just so we can see how it performed. So let's run that, and just to test it, let's just try 1, and we'll grab the history out of that. Let me know if there are any questions about this function we just wrote. Basically, this is a way for us to train a new model really quickly, just by changing one parameter. So I will say, I just want one different thing here. Oh, that was very fast. So we could say history. Let's see, loss, plt plot. Oh, I can spell. Okay, cool. This at least looks basically right. This is, as we're training, our model is getting better. But if y'all remember, we actually might want to plot, I can grab this, a slightly more advanced graph that shows us both our validation loss and our, let's remove that, both our validation loss and our training loss. So if you remember, this blue line loss, that is how our model does on data it has seen, and then how much error it has on data it has seen. And then this, is this yellow or orange? Let me know in the comments if this is yellow or orange, because I'm colorblind. But this yellow or orange color is how it's done on data it hasn't seen. And what we usually like to see is that those lines are basically pretty close. Like this one little moment right here is kind of concerning. But as long as those are pretty close, we have pretty good confidence that our model is going to generalize to stuff it hasn't seen, at least decently. Yellow, orange. Okay, we'll call it Orello, orange. I don't know. We'll call it orange. How about that? So now, if we want to, we can run this loop multiple times. And actually, I think we already have the loop basically written. Oh no. So in this loop, all we're doing in this loop, and we'll pick different numbers. We can try it for 0 hidden layers, for 1 hidden layer, for 2 hidden layers, and for 3 hidden layers. And maybe that's all we want to try. And we can see, and let's actually let it train. Let's give it a 20% validation split. So it'll have 80% of the data to train on, and then 20% of the data with 0.2 here will be used to test it. And 20 epochs is probably good. So we can now, let's get rid of this. We can now run this, and we want to test hidden layer number. And if all goes well, we should see some graphs. Okay, cool. So this is if we have no hidden layers over 20 epochs, this is how things develop. If we have 1 hidden layer over 20 epochs, that's how it develops. And you can see that here our lowest loss is 11.1, 11.4, 11.1 again. Interesting. And then that's 2 hidden layers. Oh, then we have 3 hidden layers. And validation loss of 11.3. So we can see, and I think this is actually pretty valuable to see, is that we don't actually get that much benefit from adding additional layers. And there are a number of reasons for this. But the big one is, if you come back and look at this guy right here, it's like all of this information is the first layer, but it's all being condensed into 64 units, right? So we're going from 200 times 200 is that 40,000 pixels down to, or 40,000 values down to 64, right? And so after that first layer where we process it into 64 neurons, there just isn't a lot of information that we can do much with after that. And so that is a sign that it's like, yeah, maybe we don't really need that many. Now, another thing to note is that it goes 11.1 to 11.4 to 11.1 again to 11.3. This is sort of the final score it gets on data it hasn't seen. And that's not like a straight line, right? That's like as we add layers, sometimes it gets better, sometimes it gets worse. And one of the reasons is because as we are running through this, every time we fit the model here, we might be getting a slightly different validation split. It might be shuffling the data in a different way. So one option we have actually to try to remove the effects of that. Yes, this is basically exactly right. Is it because it's mostly, for lack of a better word, compressed into one layer, that image with that image you just showed? Yes, so we have like all that information from the image, and then as soon as it gets to layer number 1, it's down to 64 neurons. And so adding more layers of 64 neurons is not, it's probably not doing that much better for us. Now you could imagine, what if the first layer was 128 neurons, and then the second layer was 64 neurons, and that's like actually an interesting thing to experiment with. In terms of architecture, I think we're going to get to more interesting stuff very fast after we finish up this. But the one thing I'd love to touch on is the trying to remove the source of randomness for what is our train and test split, because I think we know, or I believe that some of the examples here are just really tough to predict, right? Because the people are just are kind of randomly picking what they want to charge for it. I mean, in theory, we're all economists, and we're all doing price discovery. And when I list something for sale, I'm like trying to think about what is it really worth. But in practice, like, people are coming up with stuff, and occasionally people are just going to be, are just going to pick numbers that are weird as the price they're listing it for. And in that case, if we have a lot of those really weird examples in our validation set, then it's going to be really, really tough to do well on it. So a thing that we can do is just make sure we're picking the same validation set every time. So let's add a cell that says generating a consistent validation split. So we can actually take our old friend scikit-learn and use a utility from that called train test split. So we can say from sklearn dot model selection import train test split. And this is just a handy dandy tool that will take your input data and split it out into any kind of split for you, either a train and a test or a train and a validation. And so we can take the data that we're normally putting in, which is our input data and our labels, and we can say test split equals 0.2. So 20% of our data will be sort of reserved for validation. And we'll call this X train and then X test, and then Y train and Y test. Now, if you have done a bit of machine learning stuff, this will look pretty normal to you. But there are a couple of things to call out. Actually, instead of test, let's say val. So oftentimes you'll have a training set, a validation set, and a test set. And those are sort of in increasing levels of sort of importance, right? You can maybe iterate many times with your validation set, but in theory, you should only run your model on your test set like at the very end of things, because you don't want to sort of unfairly learn things about your test data. The other detail here is our X is capitalized, and this is because it's a two-dimensional matrix, or a greater than one-dimensional thing. And then our Y is lowercase because our Y is what's called a vector. It is a one-dimensional line of numbers. And so generally one-dimensional lines of numbers, or vectors, get lowercase letters, and then greater than one-dimensional matrices get an uppercase letter. So that is why we have X train and X val, and then Y train and Y val. If you have any questions about that, let me know. Emily says, yes, and when someone sells something, they usually do some research to see how much other people have sold something similar for, like the whole point of doing the ML and the CryptoKitty. Yeah, absolutely. And I think that there's one way of viewing this. Okay, we're going to go into talking head because we're taking off our ML hat and putting on our econ hat. So one way you could think about this is, on some level, every price that we could see, because these are prices of people who are currently selling a CryptoKitty for this amount. And on some level, we could say that every price we see is overpriced because none of them have sold, right? If there were any good deals, if anybody was selling a CryptoKitty for lower than what it was worth, then it should be bought very quickly. And then that would be off the market, right? And so all of the prices that you see on some level are not good enough deals to already be gone, right? And it is exactly, it's only worth it if someone will pay for it. And so if you're looking at cats that have not been paid for yet, well, then clearly no one, at least yet, no one has valued them at that. And so if you were really going to try to use our algorithm and like use it to say, find a good deal on a CryptoKitty, what you'd want to do is you'd want to get your prediction and then you want to say, okay, this is like what someone might ask for it, but a good deal would be maybe 70% of this, right? Like take that number and then say, okay, if it's 30% less than the number that I am predicting, then it's probably a good deal, right? But yeah, I think it's an interesting question on like, what are we actually doing here and what information do we have? Okay, so here we are generating a split of data. And now we can actually say our input data will be X train, our labels will be Y train, and then instead of validation split, we can say validation data and pass in our X validation and our Y validation. So now instead of it randomly shuffling and picking a validation split, it will consistently use this data that we generated. Oh, sklearn, not sklean. Train test split. Oh, what is, instead of test split, it should be, let's see if we'll get a tip here. Oh, come on. Train test size, that's what it is. Test size. Cool. Now just to verify this, if we take, say, Y train, if we get the length of Y train and the length of Y val, and if we printed them both, you see 1640. So 20% of the data has ended up in the validation set. And that's exactly what we wanted. Cool. So now we should have a sort of consistent split so that when we're comparing these numbers, they should sort of mean something a little bit more. Or at very least, we'll be less inclined to believe that that it's just random variation based on the way that we picked our split. 13.46, 13.44, 12.9. Okay, there's a little bit of an improvement. There's some benefit there. And I think we get one more. So I think the big thing to pay attention here is the axes. So sometimes just based on the way that the model is sort of randomly initialized, sometimes it takes more time to sort of like get to a reasonable place. And so you can see here, it just started out very, very wrong. It started out at 24. So the original model was just, for whatever reason, the random initial state of the model was really bad. And it took an epoch to get way, way down here. So similarly for here, it's like, oh, it was only as bad as, 14-ish. And then it started to get quite a bit better. Another thing you can say is that pretty consistently, the validation is worse than the training. And this is actually something that we would normally expect. And if you had a bigger data set, you'd be more likely to see this. But the data that you haven't seen, you're less likely to do well on than the data you have seen. And then, okay, back to 13.1. So this is a little bit more consistent where you can see, hey, 13.4, 13.4, down to 12.9, so a decent improvement. And then not way worse, but 13.1. So if I were going to pick, maybe an ideal number of layers, I might say, hey, 2 hidden layers seems like maybe an interesting place to explore more. And this is an example of an experiment we could run. I won't code up sort of submitting this, but if you want, you can try taking this information and trying a hidden neural network with 2 hidden layers, or 2 hidden layers in the middle. So you'd start with a flattened layer, and then you do hidden layer 1, hidden layer 2, and then your final dense layer that has an output size of 1. And if you want to try that, I will save and share the version. Oh, it might actually, if this is running with GPU, I might have to cancel it later. But this hopefully will publish once it runs. And you are welcome to borrow that code. I guess at this point, this is not actually better than the submission we had. So maybe it's not actually worth using. But that's a little experiment, and you can run experiments like this on on whatever thing you're looking at. If you want to see, well, hey, what is the size of hidden layer I should use? Which architecture should I pick? What learning rate should I select? That running these experiments with lots of different values. Technically, this is just a linear search where you pick a couple different numbers on the number line and try those out. There are libraries also that will sort of automate this process for you. I would say that the trade-off is with that, you have a little bit more complexity, and you have to be, because you might set this thing and it might run for several hours, you really want to be confident that when you're using one of those tools that will do, technically it's called automated hyperparameter search, that you want to be confident that that is actually going to give you the result that you want. But without further ado, let's move on from dense neural networks and check out convolutional neural networks. Why don't we? So this should be sort of publishing itself, and it might take a second. But now we can stop this session. Boom. And head back to our homepage and go over to code. And we should be able to find a notebook called, where is it? Oh, yes, Cats, Color, and Convolutions. There we go. The result would depend on the random hidden layers. So I'm not sure if which result layer you're talking about. If you're talking about the sort of the last number we're getting, yes. I mean, this is actually, there is some more meat to this conversation that we're sort of skipping over. But there's this thing called the lottery ticket hypothesis, which is when you build a neural network, obviously you're giving it the same, or at least in our case, we're trying to give it the same data every time, but you have to initialize all of the weights of your neural network with something random. And I think actually we can see up here, remember the earlier on after the first, okay, now I want to go and dig into this a little bit. So, okay, actually, I'm gonna dig into this just because I think it is a fun tangent, just to understand like really what's going on inside of the neural network. And it won't take that long, I promise. I'd say Global Hack Week, I feel like works the best. Or the Global Hack Week is better the more tangents we go on. Oh no, this is absolutely what we're here for. The more tangents, the better. Cool. So yeah, here's our very simple neural network. And actually, I don't want to. This is about to train it for 100 epochs. I don't want to train it for 100 epochs. I want to train it for 0 epochs. I actually don't want to train it at all. So our simple model, we're just going to compile it. We can see our summary. And then before we train it at all, I just want to visualize what these weights look like. In fact, okay, yeah, we just need these 2 lines of code. Oh, the model has not been built yet. Okay, that's fine. But so before we do anything, we might actually have to. Okay, we might actually have to train it for one epoch. It'll learn too much in 1 epoch. Okay, in order to just trigger it to actually build, we did compile it. Wouldn't compile involve building? Okay, we're just going to pass it the first 2 examples just to make it train in a very, very short loop. So we're not giving it a lot of, we're training the model, but we're not giving it a lot of data to train on. So it shouldn't change much, hopefully. What's the tagline? Oh, I believe the thing we talked about was relatively nerdy, relatively quickly. Okay, cool. So these are our weights. When we start, and this is technically not start, this is after starting technically, but this is what our weights are when we initialize the neural network. And whenever you initialize a neural network, these are what your weights look like. They're basically just random, and there is a reason for this. Because if we set all of our networks, all of our weights to 0, it is actually possible that our network would never actually learn much of anything. Because there's some scholarship into this, but there's a lot of scholarship in this sort of vein. But the idea is that we have randomized enough different connections that if there are any latent relationships in there, that it can pick them up, just because there are enough different connections that cover enough of all possible spaces. And there is this idea that really what you are banking on when you train a neural network is that already inside all of this randomness, already the at least initial crumbs of like a good solution are in there. Because if there aren't, then it's actually relatively unlikely with the way that we train neural networks that you are going to sort of stumble upon the sort of like perfect solution or the best set of weights, unless you have already thrown enough randomness in there that the right thing is randomly kind of in there. And you have enough weights, and this is the reason that we make neural networks pretty big, is you have enough weights that even if some of the weights are not doing like the right thing, that at very least you have enough redundancy and enough neurons that some of them, just by pure chance, will be mostly indexed on the right thing. And so as we continue training it, so now we can actually train it for a real epic. So now let's take this away, and so we're now giving it all of the labels and all of the input data for a full epic. And then let's visualize again. And so already you can see some stuff being picked out. Already it has learned that there are some connections in here, but there's still a lot of randomness. And then let's just do this maybe 1 or 2 more times just for funsies. Now we're going to train again, and we see some even more structure coming in. And this maybe we'll make this the second to last time. Even more structure, so it's kind of fleshing out the eyes, and less randomness. And then here, let's let it run actually for like, I don't know, 5 epics. We should get an even clearer picture. Yeah, I think this is a totally fair way of thinking about it. It needs something to connect to besides zeros. It needs sort of, or another way of thinking about this is that it's like you always, when you're running an experiment, you always come up with a hypothesis, right? And sometimes that hypothesis is wrong and you try something else, but you need to actually be like testing something. You can't just throw some data at the wall and see what happens. Let's see. Wouldn't it be more efficient to take a 50% transparency of the initial image to train on the neural network? So interesting thought. So I mean, I guess a couple of notes here. So one is we removed all of the transparency because we took out the alpha value. The other way of thinking about this is that really what transparency is it can be rendered in any sort of way. But really what transparency is we have RGB, and it's adding one more layer there, or one more field that is the A or the alpha value. And so really what including transparency data would do is, if we look here at our input data, and we do input data shape, it's 200 by, or sorry, it's 2000 by, so 2000 images, and then it's a 200 by 200 image, and we only have one. So this is just grayscale. So we removed actually the RGB and the A, and now it's just a total grayscale value. But so you could add back in the RGB, and you could add back in transparency. In practice, it would be an interesting thing to try. On the making everything transparent, that would just have the sort of the net impact of linearly transforming all of our pixel values. So just it would be dividing all of the pixel values by, by 0.5 or by 2. And that ultimately our neural network is kind of going to adjust for whatever we do there. So I don't think that making the entire, there's the idea of, could you include the transparency channel? So instead of having just gray, have RGBA. And so then our shape, instead of 2000 by 200 by 200 by 1, it would be 2000 by 200 by 200 by 4. And actually, this is a great segue, because what if we included some color data? Let's try it out. Well, so I would actually say I don't even think it would skew it in a weird way. And in fact, people will try what's called normalization. So trying to make all of your numbers between 0 and 1. And that's like not actually a crazy idea. Did we actually we do that? So yeah, technically here, so normally our pixel values are between 0 and 255. And here we're saying, hey, I actually, instead of dividing by 2, let's divide it by 255 so that we squish all of the values. As long as we're squishing all of them in sort of the same way, we squish everything to be in between 0 and 1. And sometimes the neural networks, for very mathy reasons, that can be a little bit nicer for them. In the same way that you don't want your weights to be initialized to 0, you actually want your numbers to be like relatively close to 0, just not 0. Okay, fun little tangent on looking at initialized weights and how they shift over time, and that's neat. But now let us jump ship to part 5, cats, colors, and convolutions. So you can, of course, always hit the edit button. Boom. And this first chunk here is basically the same. We're doing that same dividing by 255. We're importantly doing this for our training and our testing data. And now we have to manage our active sessions. So let's kill image regression with Keras. And I think it's time for cough drop number 2. Cool. So now we can transform that. This is all basically repeated from the previous one. Oh, actually, we skipped over sort of a big thing that's happening here. In the previous version of this notebook, as we imported things, so the very top here, we said CV2 IM read grayscale. So this is saying read the image as if it were in black and white, basically. And so that is throwing away all of the color information. Here, we're doing no such thing. We are keeping all of our color information. And so this just transforms our price data as well. So now we're checking our dimensions. So you can see now we're 2000 by 200 by 200 by 3 by 1. I'll repeat, this has kind of become the main idea of this stream, is that keeping track of your dimensions when you're doing machine learning is very important. So what are these dimensions? It's good to look at the shape of your matrix and be like, okay, what are these things? So 2000, that is the number of images in our data set. So it's just a stack of images, basically. 200 and 200, those are the dimensions of our image. So we have a 200 pixel by 200 pixel image, right? Because we resized them to that size. 3 is our RGB values, right? Those are our, oh no. I don't know if y'all can hear me, but I am right now. Oh, I bet I know what's going on. Oh, you can hear me. That's exciting. Oh, I'm back. Okay. Can you, am I back? Whoa. Okay. I hope I didn't give anybody a seizure there. This is, I will confess, this is my job for not treating my, I am here. This is my job, my fault for not treating my camera nicely. My camera has just been running this entire time. And I think I accidentally kicked the power source for the camera. Am I moving more slowly? I think I'm moving more slowly. But if you can hear me and see me, then maybe we'll just continue with it, even if the camera is a little bit slow. And I'll troubleshoot some issues before tomorrow. But I'm thrilled that me almost disappearing from the internet brought Red Nitro and Nanotubular back to the chat. Okay, yeah, I am. Well, I should be kinder to my camera. Where were we? Oh yeah, we were walking through our dimensions. So 2,000 images. The images are 200 by 200. 3 is the number of color channels, so RG and B, and then one right here is kind of nothing, right? If we look at this, so this is the first pixel of the first image of the this is the first pixel of the first image here. So we're first image, first row, first column is what we're looking at, and we have our RGB values, but all of them are in individual lists, or they all have their own dimension, which is kind of unnecessary, right? We don't really need that. So this is pretty exciting. This is really what we're doing, but I spaced it out to be in line with the comment here. In order to remove that extra dimension, we can say we're keeping all of the images, all of the rows, all of the columns, and all of the pixels, but just the first value in each color dimension. So basically for this list, we're just saying we just need the first thing in there. And then for this list, we're just saying we need the first thing in there. And then for this list, we just need the first thing in there. Technically, none of these are lists. They're arrays or array dimensions. And if we do this, it'll basically just get rid of that extra dimension there. And so now if we look at this same thing after that transformation, we get 0, 0, 0. That's sort of like a normal, nice looking pixel where all of our dimensions seem more or less meaningful. And then we can look at our shape, and boom, that is the shape that we were kind of expecting. So if our grayscale shape was 2,000 by 200 by 200 by 1, once we added in the RGB values, now it's 200 by 200 by 200 by 3. So it looks better. So let's just test out the TensorFlow model that we had from the last time. Let's say test size equals 2. And this is all pretty standard. Let's see what happens. Honestly, it's been a while since I've had camera issues. I got like a nicer setup when the pandemic happened, and it was like, oh, my entire life is via webcam. And for a while, it was just kind of embarrassing because it's like, oh yeah, I have this nice camera, this nice mic and everything. And like my life is hell because every time I get on a video chat, I'm like, oh wait, I need to turn on my camera and change the settings. I need to hook this thing up. Now it's kind of reached a point where it's like I can mostly just turn it on and we just go. But sometimes I'm like, yeah, I could just stream from my webcam. Like it would be fine if that's what I did. Okay, cool. So, not much better than what we were getting earlier. Not much worse either. And on the one hand, some of this might be due to the fact that we could just let it train for longer, right? It also might be due to this whole fact of like, yeah, we picked a random split here, and the random split could be different. So the experiment that I want to run here is actually by trying a bunch of different splits. And this is something that is called cross-fold validation. So we picked one split of the data to say, here's our training data and here's our validation data. But that split really matters. And so one thing that you could do is you could say, I'm going to take one split and like do the whole training process. And then I'm going to randomize everything. I'm going to shuffle all the data and take a totally different split and see how much it changes. So it's interesting to see. This is sort of like, again, with your teacher, if they're a professor giving you a test, if your professor, picks all of the hardest questions to be on the test and just puts easy ones on the study guide, that's a lot different than if they put just hard questions in the study guide and easy questions on the test, right? And so by randomizing that, you can kind of get a sense of, oh, did we just kind of get unlucky with the way that we split our data? So the thing we're doing here is we're just going to do this for four iterations. We're going to re-split the data. Interesting, we have this parameter called random state. And this is actually a really, really useful thing, especially when you are sort of doing machine learning science or data science, and you have to share your results. Being able to tell people, well, hey, when I ran this with this random seed, this is the results I got. And so you can rerun that and you can expect to get the same result again, which is very, very nice. Normally it pulls your random state from like information about your date time, or sometimes your computer will offer your OS will like offer it some random string at some point in time. But we can just say, hey, what if we start random state equals I? And so I will start at 0 and then 1 and then 2 and then 3. And so then all of this is the same. Actually, this is new. So because we're going to get to bigger models pretty soon, being able to clear our session, that basically says, hey, Keras, like stop using so many resources. And like, I'm done with this model and I'm done with the pre-existing models, and let my Kaggle environment take a break. So this will, as we run this in a loop, we'll throw out the old model and be able to create the new one. Otherwise, most of this should be pretty familiar. We're grabbing that last validation loss value, and then we're just appending it to a list so we can see that at the very end. And so these are all the exact same model. We're just trying slightly different splits, where what if this question is on the study guide and that question is on the test? And then what if we shuffled that around? So our first value, 12.6. We're waiting. Note that I've set verbose equal to 0, which is why we're not like seeing any data in the meantime. $11.8. So there's a little bit of variation, right? The model is exactly the same, and this is just from picking a different train validation split. Oh no, just had an open book 10 question quiz and got the last true false wrong. Okay, I kind of have this hot take that I think that true and false questions are, unless they're just like very, very basic comprehension checks, I think true and false questions can be very, very difficult, because it's like, okay, multiple choice, you just kind of see what the question is asking by the potential answers. But saying, is this statement true or false? It's like, well, I could really argue it either way, right? There's like a really, really high level version that I could say, well, actually, it's true. When like a basic reading of it would say it's false. So I feel you on the true false. I feel like if you're going to do a true false question, it should be like an oral exam, and I should get to like tell you that I understand the nuance here, Okay, cool. So we got a couple different values, and they range from like 11.1 all the way to 12.7. And so there are a couple different things you can do, but one option you have is just pick a data split that's like somewhere in the middle. So our second data split with random state equals 1 is like relatively close to what the average of all of these data splits happen to be. And it's not this will be true for all models. Really, all we know is this is true for this model. But we do get a sense that that if there's a sense in which some of these are like hard examples and easy examples, that this gives us a pretty nice split of there's an equal amount of hard examples and easy examples, both in the training set and on the validation set. So one option we have is just to say, let's pick random state equals 1 here, and that's like our good split. We could be more scientific, but an interesting take here. Cool. So right now we're using dense neural networks. Ooh, this is actually a good thing to check in just before we move on. And there's a 10.xxx and 11.93. And you are passing random state equals I. So I guess actually, I think Keras has a random state. Let's see. Keras model initialize weights random state. Reproducibility in Keras models. Okay, so this is actually really interesting, and I think it makes sense actually. So you got different numbers. All of them are like pretty similar to the numbers that I got. And I think this comes back to the when you create a network, there is a little bit of randomness in the initialized weights. So there's two reasons that we could have randomness, right? One is because the training data that we gave it was different because we shuffled it and we split it in a different way. And then one is because our network sort of got randomized because when you create a network, it has to be in, there has to be some random initialization. But so Keras also has sort of a notion of randomness that would lead to that difference. So we could say Keras utils dot set random seed, and that should give us greater reproducibility. So let's actually try that. I love this question because this is a thing that I have not done a lot with this, and so our numbers are pretty similar, right? They're not crazy off. I got the first one is pretty bad, or the first split is pretty bad, and the second split is near the middle, and then the third split is like the best one that both of us got, and the fourth split is pretty bad as well. And so that actually even more sort of, for me at least, like verifies that this is irrespective of the random initialization of our network. It really is just, oh yeah, are we including hard examples or easy examples in the validation set? But we should be able to do something like set our random seed for Keras to 1 and try this again. And oh no, oh yeah, we have to import Keras. Or we'd say from TensorFlow import Keras. And that'll take a second. And I'll drop this in the chat if you want to copy this, but you should be able to just kind of follow along. And yeah, I'm getting slightly different numbers from even last time, or at least this first one is slightly different, but it is in a similar ballpark, which is just cool. This is a cool little. We love staying on the tangents. Getting on the tangents is always fun. And then this one is kind of in the middle, close to your 11.8. So if you copy that into the notebook, that should be even more reproducible. But this idea that that with random, that the split we get with random state equals 1 is like a relatively average random split, that seems to be sort of continued to be confirmed. And we end with 11.9. And 11.8 is still pretty close to that average. Cool. So thank you for that additional tangent, because I had not actually interacted with Keras util set random seed, but now I have. Okay, so far, let's jump back into talking again. So far, we've only looked at dense. We've looked at the flattened layer. Oh, now I don't look like zooming in because the frame rate is bad. If I stop my virtual camera, it'll probably create chaos. Okay, hopefully y'all can still hear me, right? Apologies, stream not ended. Okay, we're back. I think it might still be, it might be a little bit better. I think it literally is, I left my camera on for 24 hours and my camera is like pissed because it's like, why would you do this? I'm overheating, I'm overworked, you don't appreciate me. And honestly, my camera has a point. But no, the stream's not ended, we're back. It seems like maybe slightly better, but honestly, if my camera has to say, no, Will, give me a break, I think my camera is probably correct here. Okay, so far we've just dealt with dense neural network layers, and dense neural network layer is really it's kind of like the Swiss Army knife of neural network layers, because in some sense it can do anything. There's actually an interesting theorem that it is like any possible function you can think of can be approximated by a single dense neural network layer, or a single hidden dense neural network layer can capture any possible function that you can think of, or any possible function that could exist. Can be approximated by this. And so it's a really sort of versatile layer to have. But in some ways, it does a lot of useless things. So for example, we have a hidden layer in our image. And because that hidden layer is dense, it means that it is looking at every possible relationship between two pixels, right? So the pixel in the top left is just as related to the pixel in the bottom right as it is to the pixel right next to it. And as just like humans with eyes, a thing that, or even humans with a notion of, of vision, we know that this is kind of a silly way to think about it, because if you're looking at an image, like the pixel right next to you is way more likely to be related to you than the pixel on the other side of the screen, right? And so this is something that our dense neural network is just incapable of really taking advantage of. And so a new kind of layer that we can introduce is called the convolutional neural network, or the convolutional layer. So this is, we can look here for a second on what's going on here. I'm trying to decide of like how much time to spend on just looking at like building an intuitive sense of a neural network, or of a convolution. Do we want to do this? Okay, let's do just sort of a very let's do like baby's first convolution. So I'm going to create an array. We'll stick to two convolutions. Oh, interesting. We even after setting the same random seed here, we got different values. That is bizarre. Oh, I wonder actually if we need to, when we cleared the session, I wonder if it cleared the seed. Maybe we actually want to say like that. I don't know. We'll let that run. It'll take a second. Oh no, we tried to allocate more memory than is available and has restarted. This is what I was trying to avoid by using clear session a lot. Okay, let's. I guess our notebook will restart. Let's just run the very beginning of this again. And then, yeah, we can stop just before we actually make any models. And let's just try to build an intuitive understanding of convolutions. So a very, very simple version of a convolution. Let's do a little matrix art. Okay, so this is just zeros here, and this is just an array of, or one row of zeros. I'm going to copy this row a lot. So this is sort of our blank canvas here. 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4, 5, 6, 7. And now we can draw. We can draw with ones. So let's add a bunch of ones here. And we're going to draw a little box just to have like a shape. And if we want to, let's call this X. If we want to, we could say plt im show x. And we should see, boom. Okay, if we wanted to say, we could say cmap equals gray. So now we get the black and white. So a 1 is white and a 0 is black. And we have a little picture here, right? So if we wanted to convolve this picture, we wanted to pass some kind of filter over it, what we'd want to do is we want to look at sort of a rolling window. And what would we do here? Actually, maybe we make let's make it actually a little bit bigger. I want to add a 0 on either side. This is what happens when I come up with examples on the fly. Is like I'm like, oh, actually, it would be cooler if our convolution did this. Let's add a bunch of zeros over here. And then let's give ourselves sort of 2 blank lines at the top and the bottom. We're going to ourselves sort of like more. In fact, actually, now that we're doing this, well, no, that's fine. That's fine. Okay, cool. So we have sort of this square, this cube, not cube. We have this square on sort of a black backdrop. So now what we could do is, in order to, I mean, one way we can think about this is in order to make this image smaller. So one way you could use a convolution is to make an image smaller. Is we could basically say, let's have a rolling window where at first we just consider these 4 pixels right here and take the average of all of those values. And then move over and say, okay, we're looking at these 4 pixels and take the average of all of their value. And then look at these 4 pixels and take the average of all their value. And keep moving that rolling window across and take all of those averages, and then that is our output, right? And that would be like, honestly, the simplest kind of convolutional window that I can think of, where you literally just take an even average of all of the pixels in your sort of window. And so we could actually code this up if we wanted to. Let's see. We could say, yeah, subsampling is like a version of a convolutional filter. Absolutely. So we can say for I in, let's get rid of this image or this warning. It's bothering me. Or we could say for, yeah, let's say for I in X until the end. And then we can say, actually, no, let's do it this way. So we'll take the length of, okay, so actually, first of all, let's take the shape of X. So it's a 9 by 9. And let's say we want to take 9 divided by 2, but we want to turn it into an integer. And there'll be, we'll end up leaving part of our image sort of lopped off. Or if we didn't want to do this, we could just make it 10 by 10 to be easy. And then let's give ourselves one more empty line on the bottom here. Okay, so now we have a square that's off center, but it's 10 by 10, which is nice. So we can say X shape, and we want to loop through the top of it. So we can say for I in range, X shape 0, integer division 2. So we just print out I. We're just going to be looping 0 through 4 here. And then we can say for J in range, X shape 1, integer division by 2, and we can print out ij here. So these are all of the, basically all the coordinates divided by 2. And so now we can sort of calculate the average of the window. So for the window that we want to get is basically I times 2. Well, now we're really getting into it here. Let's see, X from I times 2 until I times 2 plus 1, and then j times 2 all the way to j times 2 plus 1. So just to show us what's going on here, I want to set this value to 0.5 and then break. And so we visualize this. We'll visualize what range this is here, which is, the convolutional window we have, just by visualizing this again. Oh, that did not work. Let's just take a look at x. Did we not set this correctly? Oh, x isn't real. Helen says, I want a tip help on taking an image from internet, for example, and convert it into an array. Yeah, I am. We could do that in just a second. I like that as a. Oh, actually, it might be because it might not like a float. No, that is not it. That's absolutely not it. Okay, what if we just said x 0, 0, 0 is equal to 1? Oh, interesting. That's working. Sort of. Oh, okay. We just need to do +2 here. Okay, there we go. So apologies for my bug here, because indexing stops just before the thing that you're trying to the end goal. Okay, so this is our convolutional window right here that we've just spelled out. And as we go, this is going to move sort of across this. And so this is the convolutional window that we want to average. So if we take all the average of all of the pixels in here with np mean, then we can get a new value that is the result of our convolution. So just averaging everything together is, let me scroll up a little bit. Averaging everything together is sort of one version of a convolution. It might not be a very helpful convolution, but it's one version of a convolution. And that can roll across the screen, taking averages as it goes. So the new value here, we actually want to add to a new array. And we can make this new array, we'll call it new array, or new x, np array, and let's call it, it's going to be 4 by 4. So let's start it off as a 0 times 4 times 4. Well, it's actually going to be 5 by 5. And so we have our new blank array, and every time we get a new value, the new value at ij, we're going to set equal to this new value. And when we run through that, so this is our new x. That's not exactly what we wanted to see. Why does new x look like that? That's a bit peculiar. Well, I think this is a testament that I should not come up with random examples on the fly. Oh, because I already actually I overwrote our original array. Maybe that has something to do with it. Oh, also actually is because all of these, again, are integers, and really we should have made them floats. Okay, let's see. As type float. And our new one should be as type. Okay, here we go, finally. And boom, here we go. This is our convolution from our, starting with our 10 by 10. We have now condensed it into a 5 by 5 with some sort of additional information. And you can see we've kind of sort of softened the corners, and this top left one is a little bit brighter, and this bottom right one is a little bit softer based on the way that we were aggregating. But that is a convolution. I don't know how much that helps you sort of conceptually, but that is a convolution. Someone asked, how can we take an image from the internet and convert it into an array? And I mean, one simple version of this is we've sort of already done this with our CryptoKitties. So if you look at, inside our file here, we have just, PNGs. And so you can just download a PNG from the internet, and you can use CV2 IMRead image path. And then you can get that image data if we just look at IM here. Oh, IM is not defined. If we look at train images 0, that is a matrix. And if we say PLT IM show, we can render that matrix as the original image. Oh, it doesn't like that. Invalid shape. Oh yeah, because we needed to remove that last dimension. I forgot about that. If we come back to after we get rid of that extra dimension, train input data, and we say PLT IM show, still not pleased with it. That is a long error message. That looks right. Say PLT. Oh, not PLT. We're using PLT IM show. We were. Oh, error and callback. Unsupported D type. What is the data type of our training data? It's an array. I will confess, I'm not totally sure what it's complaining about. Shape of this. Yeah, it's 200 by 200 by 3. Just import matplotlib. Draw all if interactive. Oh, I wonder if sometimes matplotlib attempts to do too much. Sometimes if it knows that it's in an environment where it might have some like interactivity, like a notebook, it'll try to do extra stuff. I believe this is an issue with us trying to do this in a Kaggle notebook. So I'm going to restart our cell or restart our notebook. I'm not certain this will fix this. But also, Helen 1900, if you have an image from the internet, like a link that you want to drop in the chat, I can use that as an example. Like if you just paste the URL, or I can grab a random one. Let's see, what do I want an image of? An image of a capybara. Let's see. Pixelated capybara. I want like a small one. In fact, actually, let's filter tools. I want images. I'm gonna look for like a really. That might. Oh, you see, it's pixelated, but it's also too big. Nah. Okay, we'll just take a regular sized capybara. We'll just take a photo. So we can open image in new tab and interesting. That's a URL that scares me. If you can find a URL that ends in like PNG or URL, that's usually a good idea. Oh, user's right. Open image in new tab. There we go. Ends in JPEG. We'll grab that one. Oh, you want a black and white image? Okay, fine. Even a black and white image is probably going to have color data. It'll just be like removed. Let's just go with this for now. Actually, this will be okay. So the first thing we would want to do after this is started back up. See if this is cooperating. No, it's still okay. We have to debug this, but mostly, I don't want to get too. We have to debug this first, actually. Import requests.get. Actually, to download an image from a URL. Okay, just the downloading of images from the internet is going to be a little bit. I'm going to say it's a little bit outside of scope of this stream. So I think, unfortunately, we're going to have to leave that one. I do want to solve this bug, though. The error in callback draw all if interactive Kaggle. Oh, interesting. This is saying data that had not a number in it. Or matplotlib inline. Let's try that. That seems simpler. No, not fixing it. Do we have any data in here that is not a number? Check if a NumPy array has any nan. Oh, is nan method. No, that's what I tried. Maybe npy is nan. Not sure all looks false. If we sum that up, we should be able to see if any of them are. Yeah, so it looks like all of our data is still good. But that just started having errors. Interesting. Let's try the internet again. Kaggle, notebook, error in callback. I don't want to spend too much time just trying to debug this matplotlib issue. That doesn't sound like our problem. Okay, well, we have our basic example of a convolution. Does this still work if I just... that still works. So it's something about maybe how we were importing our data. That's 200 by 200 by 3, and that should be imminently plottable. But it's going to complain about it, I guess. Well, this will be a bug for another time. Maybe tomorrow I can weigh in on if I figured out what's going on there. But so let's get to the actual convolutions because that should work for us. So we can take something like the original network that we built, and we can add some convolutional layers to it. And I'll start with one convolutional filter. So this layer, convolutional 2D, does what we just saw, where you kind of move a sliding window across your matrix, and you take the average or some other function of all of the information in that, and that's what you pass up. And so this will have this sort of sliding window, and we can tell it what kind of sliding window to have. So we're saying exactly one sliding window, and make that sliding window a 3 by 3, or the kernel is sort of the thing we're talking about, and make that kernel a 3 by 3 window. So it'll look at 9 pixels at a time sliding across the image. And the activation function shows sort of how it propagates forward information. And we do something called max pooling. And max pooling it's kind of similar to convolutions, except it's kind of like we did up here. Instead of taking the average, it just takes the maximum value in that 2 by 2 pool. Then our trusty friend flatten, and then a dense layer, and then our final dense layer to give us the sort of answer. And then we'll call this CNN model for convolutional neural network. Our loss stays the same, our optimizer stays the same, and now we'll use that XTrain and XTest data, and we'll see what happens. Oh, TensorFlow is not defined. Well, we should define it. Where did we first import TensorFlow? I guess up here. Oh, actually, we'll want to generate that as well. I know we had like I don't know, it felt like we had a good tangent there, and then we got on kind of a less good tangent that specifically there were bugs, which is always not a fun time. But any additional questions? And we're training, and we're training. And we finished training. And we're down to 11.4. So interesting to compare that to our dense neural network up here, where, okay, we got further than 11.4 up here. Or really we care about this giant experiment, which I believe it was like around 11.4. But it looks like we could actually, well, let's plot the loss. Oh. So it looks like we're still kind of making progress. So maybe we try letting it run for longer than 20 epochs. Actually, one thing that we should do is we should look at the summary of this. So 313,000 neurons, and I guess our hidden layer here is kind of small comparatively. So what if we beef that up to 128? And let's try it instead of for 20 epochs, let's let it go for 50. See what happens. Okay, nice. So we've already broken through that layer of like the 11s. Now we're in sub 11 territory. But it's floating up around there. Cool. So now we're up to like 1.2 million parameters. Let's look at this. Okay, cool. So this is, I love this graph because this graph just really, really clearly shows sort of the moment where we started overfitting. And so you can see that we were doing pretty good up until about 10 epochs. And then we started getting a little bit chaotic and we started overfitting a bit. And there was that really nice period where we really were under 11, which is the best we've done so far. So one thing I want to try, first of all, it looks like we don't need to train this past 20. Like 20 would be probably more than enough epochs. But something I want to try is adding a layer of dropout. So what's going on right now is it's overfitting to our data. And if we add a layer of dropout, gf.keras.layers.dropout, what this does is it functionally, I mean, literally, it with whatever percentage we add, so here 20%, it gives a 20% chance of just zeroing out whatever a neuron says and saying, you don't get to look at this neuron. And the effect of this means there's enough randomness in the layer feeding forward that it makes it hard for our network to sort of just like memorize individual things. And the science here is super cool, but it sort of forces our model to have more distributed representations, which tend to be more robust and more generalizable. So adding a layer of dropout might help, but then also let's lower this down to 20 because I imagine that's actually up our 0.2 for dropout is maybe fine. And let's give that a shot. Oh, layers plural. Okay, here we're still progressing. Something you'll notice is the dropout is actually on some level it's making our progress slower. It's making it harder because it is adding that noise. But it should mean that we are ending up with sort of a slightly more robust model. You can see that our dropout layer actually has 0 trainable parameters because it's just adding randomness. It's not actually changing anything. And that's tough. It's like, oh, if we had run for a little bit longer, would it have done better? I have 20 epochs, so not that. So what I changed here was I added dropout, and I increased the number of dense units here to 128. And we were briefly sort of in sub 10 territory. Another thing actually that I think is going to be very powerful is increasing the number of convolutional filters. So here we only have 1 filter going across, but what if we had 8 filters? And the intuition behind having multiple filters is that each of them can pick up a different kind of feature. So there are interesting studies where they look at what these layers are doing, and they can visualize like, oh, this one convolutional filter is really good at picking up sort of vertical lines. And this filter is really good at picking up curves. And this other filter is really good at picking up sort of like a particular kind of texture. And so by giving it more filters, this might give it, I mean, it is going to increase the parameter count, not by that much actually, but it might give it the ability to sort of index on even more nuanced features of our image. We really do, for whatever reason, get into overfitting territory here. I would say for whatever reason, we kind of know. One option is to up the dropout even more to 0.5. And this is, of course, something that you could be a little bit more methodical about. You could, of course, run this in a loop across several different parameter configurations and try. So with that increased dropout, the sort of the progress we're making on some level is even slower. So now I kind of want to let it run for a little bit longer. So again, we could be more sort of scientific here, but it is also often quite fun to fiddle. Another thing to note is that our data set is only 2,000 images. And in the world of machine learning with image data, 2,000 is honestly a pretty small number. 2,000 is not a large data set. Uh, Dopefish lives. How does MLH make money? I've always wondered. This is a great question. And there is like an entry in a handbook on like here's like the proper way to respond to this question. There is a mix of stuff. I know a lot of it comes from sort of tech companies that want sort of either adoption of products. So I mean, this is the classic thing that I believe the Google Cloud, maybe they're not still a sponsor. At some point, Google Cloud was a sponsor of MLH. And so whenever MLH went to a sort of physical hackathon, they would give MLH cloud credits. And like it was this win-win because MLH wanted cloud credits for hackers, and Google Cloud wanted a bunch of students to like try out Google Cloud. And for that privilege of distributing cloud credits, Google paid MLH money, and so that's like one basic level. So there's sponsorship money, working with sponsors. There's also employment. I know there have been a couple of programs where MLH has sort of done. I believe it's the fellowship program where you basically have sort of an internship with MLH, but then if you do really well at that internship, you can get hired by a company. And the reason that the company would want that is because it's sort of like an extended interview. So there's sort of like an HR arm to it too. I'm honestly not the best person to answer this question, but that's like the main couple of things is like, oh, I want more people to know about my product. I want talented young hackers to hire, and so companies can work with MLH and give MLH money, and then MLH engages with the community. And so at the best scenario, it's sort of a win-win-win. You also have, I think, a lot of coaches that are not strictly doing things for the money. It is a certified B Corp, which is sort of an interesting dimension. So it certainly is like there's not a super strong sort of profit incentive, which I think lets them do things that are not going to be as not demand the sort of return on investment that you might in a different kind of company. How to get an internship at MLH. Okay, so we're getting off topic, but I believe this is on let's see, MLH fellowship. Boom. Apply now. There you go. Oh, that has an ID, so I will not copy that. But yeah, fellowships.mlhio. No, it's a good question. It is like MLH is not a there's not a product that MLH sells in a sense where you can really point at something, Okay, so maybe we're feeling better at this. We're not getting overfitting, which is like it doesn't seem like we're really hitting that point where it's still a little bit noisy, but we seem to be in the clear there. And I think this is about the best. 11.1 as like a validation loss that we have some more confidence in. Yeah, it looks like the best before was like 11.2. But we're certainly as we're doing more things here, we're getting sort of diminishing marginal returns. So maybe we will quickly use our convolutional neural network and make some predictions. And so we fit on X train and Y train, and we should be able to predict on, let's see, is our X, or is it test input data? Is that what we got? Yes, test input data. Great. And we should be able to put our predictions right into price in our test DF if all things go according to plan. Oh, that was fast. Let's do head here just to make sure things look okay. Whoa. Cool. Those all look like reasonable numbers. Actually, this is kind of cool. I want to do a histogram here. With our previous model, we were getting a lot of negative numbers. And it looks like basically here, we're getting no negative numbers, which is really, really nice to see. So that's pretty cool. So now we can just grab out of our test data frame just ID and price. So we get our submission, DF, and then submission, DF to CSV, we can say submission.csv index equals false, so it doesn't give us that random index, like additional ID column. And that should work. And so now sort of for our last thing we'll do, I want to come and comment out things that we don't actually need. So like this whole training loop, I think we don't need. This training we also don't need. So this should now run relatively fast now that we've removed some stuff. Oh, actually, the one other thing that we can do is our training here. So we obviously wanted to test it with our validation split, but for our actual final submission, we want to train on as much data as we have. We don't want to leave any data sort of waiting. And so what we can do is we can, instead of X train and Y train, we can say train input data. And I think we called it train labels. We can still have the validation data there. That's fine. But let's try running this to make sure that works. And in theory, we should get even better performance if we are, oh yeah, look at that. Yeah, even better performance if we're using all of our data. So that looks good. And so now let's go ahead and submit this and see if we get a positive submission. Can you suggest some project ideas on ML which can uplift resume? Yeah, I mean, I think if you're looking for something that is relatively high yield on your resume, the place that my mind immediately goes is working with fine tuning. So if you're not familiar with Hugging Face, Hugging Face is a great sort of library and platform for large language models. And so I've done a number of projects in this space where you take you take GPT-2 or you take Llama and you fine tune it for a specific task. So I fine tuned a model for writing science questions. In fact, this is actually on Kaggle right now. If you go to LLM Science Exam, which I think is on the homepage, there we go. So this is like my big Kaggle project that I've been doing, and this is based on a Hugging Face model that I fine tuned. And I think that is like a thing that right now people are very drawn to. So I would very much recommend getting into fine tuning models. I think it's much less important to know how to train from scratch a large language model, but it is, I think, much more important and compelling to be able to take a pre-trained large language model and to be able to do something interesting with that. Okay, so 2 minutes, that seems, reasonable. It's probably going to take a couple minutes. Hugging Face is cool. I think Hugging Face is cool as well. I mean, in a word, the suggestion is like learning about fine-tuning large language models with Hugging Face. I think there was something called Elastic, I think, for doing Global Hack Week. This is like Elastic with LLMs. I remember there was Elastic Security, and that is actually something that I like, or like Elastic Stack. It's something that I did a few sessions on way back when. Yeah, I don't know. Oh no, there was an error. Okay. Well, we're right at the end, so we might have to. Oh, okay. It was the same error, and did it stop running because of that? Oh, did it not submit because there was that error? The error isn't even our fault. Okay, well, we can comment out that error that we didn't really care about. Yeah, we don't need this. Let's try submitting again. Elastic.co. Oh, this was just in response. Okay, yeah, this is sort of the Elastic stack. Yeah, is this speaking to the question about how does MLH make money, or is this about like a project to bolster one's resume? A model for something. Interesting. Well, I am sure. I mean, I guess this is to the point about the resume thing. Is like, oh well, everybody is like every tech company has to have an answer for like, hey, how are you connected to AI right now? And I mean, there's some companies that like are sort of like ML first companies, and there are a lot of companies that like aren't but have to have an answer. And I don't want to besmirch anybody. I'm not not here to throw shade. My general understanding of Elastic is that sort of like the main thing that they have historically done is is a lot of it is like observability and like being able to let you host a solution to ingest a bunch of logs. Which I mean, I can totally see the tie-ins if you're if you build a platform to to ingest a bunch of text data, then like this is a pretty natural fit for large language models. But I cannot say I know anything particular about the model training situation there. Observability, yeah. Allegedly, that's what I do. My job is kind of an observability job. Oh, hey, heck yeah. Look at that, y'all. This is us making progress. This is progress right here. Incredible. So by submitting that, I got a 10, which is, I think right now, if we look at the leaderboard. Okay, yeah, that's right up there with the best scores. So, I guess on that note, I think we'll leave it there. I know we actually are about to be booted anyway. But thank you all so much for being here. Oh my goodness, did I already give the feedback form? I don't think I did. Day 4 feedback form. If you have made it to the end of this very meandering session, then I would really like to hear your feedback because you are, as we like to say, the core squad. Emily said didn't move up at all with that notebook. That is, I'm sad to hear that. I think my version should now be published, and so feel free to try mine as well and see if that improves. I know I played around with these parameters a little bit that may have been ultimately helpful. Do we need to resubmit if you filled out yesterday? No, I mean, so if your feelings have generically not changed, no need to resubmit or to submit to the feedback form again. The big thing I will say is that we're down just to our last 2 glitter colors. So if you want me to wear silver or green glitter tomorrow, if you don't care, then that's totally chill. No need to fill out. But if you are interested in picking what color glitter I wear, then yeah, you can vote on that now. All right, on that note, final reminder, actually, how much longer do we have on the data? Okay, yeah, so this will close. I'll make sure that it doesn't close before our session tomorrow. But yeah, my code should be public now, so if you want to go and look at that and muck with it, you are more than welcome to. And this is a part of it where you really just kind of can mess with that architecture, mess with the parameters, try out different things. And see what works. But the 5 ways to win a swag drop are to be first place or second place on our leaderboard. Oh, actually, did I change this? I wanted to make sure that there are some folks that have submitted to the competition that I don't think are like part of Global Hack Week, which is totally cool. But like, I don't want to give a swag drop to someone. Oh yeah, so I asked for your Kaggle username in this form, and specifically, I'm going to give sort of like priority for swag drops to people that are like fill out the form and like are part of Global Hack Week, because I don't want to give swag drops to people that are just like random Kagglers that are like submitting for for kicks and giggles. Anyway, when this is over, I will make sure it finishes. I'll update. I think it might end tomorrow. I'll make sure it ends on Saturday, so everybody gets a little bit more time to work and submit after the stream tomorrow. But yeah, so being first place or second place, let me know your username in the feedback form so I can prioritize people that are actually on stream. The best discussion, best code submission, and and then a raffle of all the people that have submitted that are contributors. If you have any questions about that, let me know. Otherwise, I will sign off. I had some interesting goodies from MLH. How to get those? Yeah, so those are the 5 ways. Is be first or second place on the leaderboard here. Try to strike up a conversation or discussion that is top notch. Publish some code. So code that is public, I will consider for the code consideration. Or if you submit, I will randomly select someone from the leaderboard. On that note, I think that is all we have to do here today. Thank you so much for attending. It was so good to see all of you. And we will be back here tomorrow, 1 hour earlier than today. And we will look at some observability and looking at sort of different architectures for a neural network besides just our standard sequential model. Thank you all. Take care, and I will see you tomorrow.